مصنوعی ذہانت کے بارے میں ایک زمانے میں ہم صرف کتابوں میں پڑھتے تھے، سائنس فکشن میں پڑھتے تھے، یہ کوئی دور کی چیز تھی. لیکن وہ زمانہ تو اب آ گیا ہے، اب ہر طرف یہ دکھائی دیتا ہے. اب آپ دیکھیں کہ ایئر لائنز اپنے شیڈیولز اے آئی سے طے کرتے ہیں. مینوفیکچرنگ میں اے آئی جس نے نہیں لگایا ہے اپنے پلانٹ میں، اس کا کاروبار چل نہیں سکتا. ڈاکٹرز اب اسپیشلسٹ جو ہیں، ایکس رے چیسٹ اسپیشلسٹ، وہ پہلے اے آئی کو دکھاتے ہیں اور پھر جب اس سے تصدیق ہوتی ہے تو تب اپنی رائے دیتے ہیں. یہی بات اب آپ سمجھ لیجئے کہ دنیا کے، ہماری زندگی کے ہر شعبے پر اب صادق آئی ہے. جو جتنا زیادہ انڈسٹریلائز معاشرہ ہوگا اتنی ہی زیادہ اس کی مانگ اور وقت ہوگی. اور جو اتنے انڈسٹریلائز نہیں ہے لیکن جو آگے بڑھ رہے ہیں، انہوں نے بھی کچھ ایسے انسینٹیوز دیے ہیں اے آئی کے لیے، اے آئی حاصل کرنے کے لیے، کہ ان پہ غور کرنے کی بھی ضرورت ہے. تو یہ آج کا جو موضوع ہے، آرٹیفیشل انٹیلیجنس ان پاکستان. آرٹیفیشل انٹیلیجنس ان سعودی عربیہ بھی ہے. ایک بہت مشہور روبوٹ ہے صوفیہ کے نام سے. صوفیہ کو وہاں کی شہریت دی گئی، بڑی خوبصورت لڑکی نما روبوٹ ہے. اور خیر وہ آپ کو اور مجھ کو شہریت نہیں دیتے، لیکن اس روبوٹ کو دے دی، جس کی بعد ادھر بہت سے سوال اٹھے. کیا یہ روبوٹ مسلمان ہے؟ اس کو تو سارا قرآن حفظ، اب حفظ کرنے میں کیا ایک چپ لگتا ہے نا. لیکن وہ بول بھی سکتی ہے، وہ چل بھی سکتی ہے. اس نے انٹرویو بھی دیے ہیں بہت بڑے بڑے اینکرز کو، اور کچھ کی رائے یہ تھی کہ ہاں یہ تو بہت ہی سمجھدار قسم کی خاتون ہے. بہرحال اس کے اوپر ایک رائے لوگوں نے الگ الگ اپنی رائے دی ہے. ہاں یہ ایک بہت بڑا موضوع ہے، اور ہم چاہیں یا نہ چاہیں آرٹیفیشل انٹیلیجنس تو اس دنیا میں آ گیا ہے، اس سے آپ بچ نہیں سکتے. تو آج جس موضوع پر ہماری بات ہوگی، آرٹیفیشل انٹیلیجنس ان پاکستان، ہمارے جو اسپیکر ہیں عباس رضا، میں ان کے بارے میں تھوڑا سا آپ کو بتاتا ہوں. عباس پہلے امریکہ میں ہوتے تھے، خیر پیدائش ان کی یہاں کی ہے، پاکستان کی ہے، کراچی کی ہے. پھر وہ کولمبیا یونیورسٹی چلے گئے، فلسفی پڑھی، اور اس کے بعد پھر وہ اٹلی گئے. اٹلی جا کر انہوں نے ایک میگزین شروع کیا، 3 کوارکس ڈیلی، جو اپنی قسم کا ایک منفرد قسم کا جرنل ہے. اور بس آپ کلک کر کے دیکھ لیجئے تو آپ کو پتہ چلے گا کہ کس اچھے ہائی کیلیبر انٹلیکچول مضامین اس میں چھپتے ہیں. اور جس کا تعلق انٹلیکچول مسائل کے ساتھ ہے، وہ ظاہر ہے کہ قدرتی طور پر وہ پھر آرٹیفیشل انٹیلیجنس کے بارے میں بھی متجسس ہوتا ہے. تو عباس نے پھر آرٹیفیشل انٹیلیجنس پڑھنا شروع کیا. تو میں نے پوچھا ان سے، میں نے کہا کہ اس کی میتھمیٹکس بھی آپ نے پڑھی؟ کہتے ہیں کہ ہاں میں نے ٹھیک ٹھاک پڑھی. بہرحال اب میں زیادہ وقت ان سے نہیں لینا چاہتا. تو عباس، آر یو دیئر؟ آر یو واچنگ اینڈ کین وی اسٹارٹ؟
I am indeed here,
اچھا
Parvez.
دین
Thank you for that introduction. Yes, I am ready.
okay, good, then I'll pull the screen down. And the projector has started, so I will then listen to your lecture. And then when the lecture is over, then we'll have a short conversation, and then you can have a talk with the audience and tell them what's in your mind.
Yeah, inshallah. Assalamu alaikum to everybody. And سب سے پہلے تو میں یہ کہنا چاہوں گا that I have had the privilege of having Parvez Hood bhai as a respected mentor and also I must say a friend for over 30 years now. So the first thing I would like to do is to thank him. I feel very honored to be speaking with him and to all of you. Today I'm going to speak in English. उर्दू वैसे मैं बोल सकता हूँ, मगर जिन चीज़ों के बारे में आज गुफ्तगू हम करेंगे, I don't have the vocabulary in Urdu. I'm sorry. I left Pakistan at a somewhat young age, so we'll be speaking in English. Let me just give you a little quick overview of what I'll be talking about. I'll give you a little background about myself. And then I want to give you a little bit of a history of AI and how it has developed, especially neural networks and deep learning. And then I will give what I hope is fairly accessible but not too simple explanation of how it actually works. And then we'll talk a little bit about the societal implications for what the advent of AI might mean for everyone, but particularly for places like Pakistan. And lastly, I will be stressing the tremendous opportunities that AI offers, and I will be encouraging you to engage with these tools so we can together produce a good future for Pakistan as well as for other places. I plan to speak for about maybe 40 minutes or so, roughly, and then we can have a discussion. I will be speaking from some notes and texts that I wrote down over the last couple of days in preparation for this talk. So let's jump in. With my background, I have a degree in computer science, and which Parvez didn't mention, but actually I did my undergraduate education at Johns Hopkins University in Baltimore. And I took my first course in artificial intelligence in 1984, I believe. At that time, Terry Sinofsky, who is now considered one of the grandfathers of AI, was a connectionist pioneer, researcher. Connectionism is the theory behind these deep learning neural networks that you see these days. So my interest in AI, I was fascinated by that course, and my interest goes back to more than 40 years, and I've kept up that interest and have also, my primary other interests have been in related fields like neuroscience, evolutionary psychology, and as Parvez mentioned, I have a couple of graduate degrees in the philosophy of mind and language from Columbia University in New York. So I'm the kind of person who reads a lot of books on his own also on these subjects, and you could say with some fairness that I've been mildly obsessed with thinking about intelligence, both artificial and human, for most of my life now. So in the last 2 or 3 years, the AI world has started moving so quickly and dramatically that that's when I decided that I needed to refresh some of the mathematics, the models that are currently being deployed, some of which I'm sure you've heard of, ChatGPT, for example, or Google's Gemini, or Anthropic's Claude. They use, as you will see when I explain how they work, they don't use cutting-edge mathematics, but they use a fairly sophisticated level of mathematics. And I have tried to refresh my own background to relearn some of that math. In addition, I have taught myself about the various architectures which modern artificial neural networks employ. And I have also been following very closely the commercial products, which including all the frontier models, which have come out of in the last couple of years. And these days, they are advancing so fast that almost every week there are some new releases. In the past week or 10 days, OpenAI has released their new O3 model, which is a reasoning model, and so on. So it's China, of course, is in this game also with their DeepSeek models and so on. But I have been trying to keep up with these developments as they happen in the last 2.5 years in particular. Although, as I mentioned, it's been a lifetime interest for me. So, I want to talk a little bit about why and how AI has suddenly just exploded into public consciousness in the last couple of years. I think the major turning point came at the end of 2022, just over 2 years ago, which is hard to believe that it was such a short while ago, when a company called OpenAI released a much larger and more capable AI model than anything that had come before that. This was GPT-3. GPT, by the way, stands for Generative Pre-trained Transformer. Generative meaning it can generate language. Pre-trained means that it goes through months of very intensive training, which I'll be explaining. And the word transformer refers to a very particular architecture of neural networks that was invented in 2017, and that lies behind pretty much every single one of the frontier models, which are the most advanced state-of-the-art models at the moment, whether they come out of China or the US, which are the two, by the way, the two leading places for research in these kinds of models. So suddenly we had, OpenAI made this GPT-3 available in the form of a very friendly chatbot interface called ChatGPT, which the general public could interact with. And suddenly everyone could experience firsthand what interaction with a very powerful AI feels like. You could just type in a question or some other prompt and get very perfectly formed, coherent answers to your questions, stories, explanations of difficult concepts. It wasn't any longer just a tech demo for specialists, not something just for engineers to deal with or to write academic papers about. It was right there on our phones, on our laptops for anyone to try. And the effect of that was dramatic. In public terms, AI went from a niche topic to a mainstream topic in the news almost overnight. Various media outlets were publishing story after story about it. I think it was in February of 2023 that Kevin Roose wrote what has become a very famous article in the New York Times, about a very strange and unsettling experience he had chatting with an AI. In fact, it was Microsoft Bing chatbot based on an earlier GPT model. But during the conversation, amongst many other strange things, the chatbot told Kevin Roos that it was in love with him, and eventually in the conversation tried to convince him to leave his wife. it became it became quite famous because people were understandably a little bit freaked out by what are these things? Do they really understand what they're saying? What is this technology? Is it safe? And so on. So in the last, before this, AI had been progressing and becoming more powerful, but it had not become so accessible to the general public and so present in our collective public consciousness as it has in the last 2 years. And a lot has happened since then, which I'll be talking about a little bit more. So I want to give you just so you have some sense of where these things are coming from, that it's not magic. There is a history behind this, the way, I mean, it was in the 1950s that people started speaking about, soon after the invention of computers and the very first computers were built, people realized that we may be able to one day make them quite intelligent. And so AI as a field goes back to the 50s. And there have been two main paradigms that have been followed. Both were thought about in the early days, in the 50s, and I'll tell you about them one by one. The two main approaches to AI are called symbolic AI or neural networks. Artificial neural network is the second way of approaching artificial intelligence, or how to make machines intelligent. So let me tell you a little bit about symbolic AI first. This was really the dominant approach from the late 50s well into the 1980s. And it's based on the idea of explicitly encoding the kinds of knowledge that we have, the kinds of logic that we use into a computer. In symbolic AI, you would handcraft rules and code in facts. It's a bit like trying to teach a computer how to think by programming in all the common sense rules about the world, like objects fall down, they don't fall up. But you must teach a computer this. It doesn't know it by itself. You might try to teach it logical syllogisms of like, all humans are mortal. Socrates is a human, so that it can deduce Socrates is mortal. So this approach treats AI like a giant logical system. You feed in facts and rules, and the computer uses logical inference using those facts and rules to try to answer questions or solve problems intelligently. And there were some successes with this approach, but in limited domains. So, for example, expert systems were built that could do useful things in, as I said, in limited domains. So there were some symbolic AI programs that could diagnose medical conditions by following decision trees of symptoms and test results and rules. Or a famous example that you might be familiar with is chess playing programs, which had the rules of chess built in, could follow. If I make this move, that makes possible the following number of moves for my opponent. For each of those moves, there are this many numbers. And of course, that number explodes into vast numbers very quickly. But computers could do this tree search by brute force with a combination of some heuristic rules that were built in to the system. One such symbolic AI program called Deep Blue for the first time beat the reigning human champion Garry Kasparov in 1998. That's 27 years ago. That was also a symbolic AI product. So, and there were other projects of this kind. There's a well-known computer scientist named Douglas Leonard who tried to build a massive common sense knowledge database called the Psych Project, trying to encode millions of everyday facts about the world. And I think he tried to recruit a lot of volunteers. There was a language developed into which you had to present these facts to the computer, to the database, and volunteers would come in and just do this. But ultimately, this kind of approach hit a dead end. It turned out that it's incredibly difficult and tedious to anticipate and explicitly code all kinds of, all the knowledge that we have about the world that we learn through experience. This was turned out to be not really easily possible. The world is very messy, it's very complex, there are always exceptions to rules. The amount of knowledge we take for granted, even in a simple conversation, actually turns out to be quite vast. So symbolic systems were brittle outside the very narrow domain they were programmed for, like, for example, the chess-playing computer that beat Garry Kasparov. They fail. And so by the late 1980s and well into the 1990s, progress in symbolic AI had slowed to the point where people started referring to this period as an AI winter. There was a lot of disappointment, reduction in the funding available for research for AI when these systems really failed to deliver on the promises of intelligent machines. Which brings me to the second major approach to trying to make machines intelligent. And this is based on what little we know of how the brain works. Now, let me just abandon my notes for a second and tell you something about what we know about how the brain works. It's not a lot. We know at a very low level how things like neurons function and how they are connected together through axons and how there are synapses and how these synapses have weights and how action potentials travel a neuron can fire with what's called an action potential, and that travels down an axon and then feeds into the next neuron, which may or may not fire depending on how many of its inputs are getting a signal. And so at a very microscopic, small level, there's a fair amount that we know. We've also been able to study the brain at a fairly high level. So systems like vision, for example, and how images are formed on the retina, what signals go back through the optic nerve, where they end up in the visual cortex, which is in the back of your head, and how, where edges are detected. Some very high level things like that are known through experiments and also through malfunctions of those systems. If you have a stroke, which destroys a certain part of your brain, it takes away a certain very specific ability you had. So now we know that that part of the brain was doing, making possible your ability to do that thing, and things like this. But we don't really know how the middle levels of the brain work. So by mid-levels, let me explain again by analogy. It's a little bit like if you knew how you can form NPN junctions in silicon, which can function as transistors, and you also know how to use Microsoft Word on a computer, but you don't know how the transistors are connected together into digital logic gates, how digital logic gates are connected together to form mathematical or other digital functions, which in turn form an instruction set for a computer, which is called machine language, on top of which comes something like assembly language, on top of which come higher level languages and things like operating systems. And these are the middle levels of a computer that you would know as a computer engineer, but you would not know if you know how to use Microsoft Word on the one hand, and know how transistors can be formed using doping of silicon on the other hand. That's the kind of situation we find ourselves in with human brains. How the mid-levels are organized hierarchically, the way we do know how they are in computers, we don't know. So that's just an aside, sorry, about, I was about to talk about how neural networks work. This is the second approach to intelligent machines. Now, these are inspired by the low-level functioning, what we do know about the human brain, how neurons work, how they're connected together, and so on. And as I said, the concept has been around since the 1950s, but it was difficult to get collections of artificial neurons connected with weights, the way we understood the human brain to function at the lowest level, to do anything useful. But basically, we tried to mimic what we do know about the brain. So artificial neurons also have a certain level of activation. They don't have spikes like the human brain, but they have an activation level. They are connected to other neurons by links which have weights, which is very similar to how certain synapses have weights in the human brain. So each artificial neuron takes some inputs from connections to it, does a little calculation, and produces an output which goes out to connections to every neuron it has in the next layer of neurons. the weights are basically numbers that determine how strongly one neuron's output will affect the next neuron. So we do know that in human brains, and as well as in artificial neural networks, knowledge is encoded in the weights of these connections. So I've been saying a lot of things which are probably difficult to understand, so I'm going to try to explain by example, and it's a classic example because this is one of the first successful artificial neural networks which was built in 2012, which really changed the paradigm from symbolic AI to neural networks. Let's imagine that your problem is for a computer to try to recognize handwritten digits. Now, there are 10 digits, 0 through 9, and different people write them slightly differently, and it's not a trivial problem for a computer. For us, it's not that difficult to recognize most people's handwriting, although I leave doctors aside. They have famously bad handwriting. So what you do is, let us say we have a low resolution 20 by 20 pixel representation of a handwritten digit. So this would be 20 by 20, 400 pixels. So the input to this neural network would be a set of 400 neurons in one layer. Then there are some hidden middle layers of neurons. And then there's an output layer, which gives you the answer. You are giving it a picture, 20 by 20 pixel picture of a handwritten digit, and you want the output to be, there will be 10 neurons in the output, representing the digits 0 through 9. And you want the correct one to light up, to have a high activation. You want the other ones to have very low activations. Usually, the level of activation of a neuron is between 0 and 1, and so it can be interpreted as a probability. So, for example, if you sent into the input an image of the digit 5, you want the number 5 output neuron to have a value near 1, and you want all the rest of them to have a value near 0. That's how the neural network tells you that what it has seen is a 5. So how does it do this? There may be many layers in between of many neurons. So remember, there were 400 neurons in the input layer in this example. Then there is another layer of various numbers of neurons. There may be, let's say, 6 layers in between, and then the output layer. Each neuron from the first input layer is connected to each neuron in the next layer. And then again, the same way. Every single neuron in the second hidden layer is connected to every neuron in the third layer, and so on. So the number of connections multiplies very, very quickly. If you had just a few hundred input neurons and 16 neurons in 2 middle layers, and then the 10 output neurons, it would already be something like on the order of 15,000 connections. So what you want to do is somehow change the weights of those connections so that when it sees a 3, the number 3 neuron lights up. How do you do this? There are so many thousands of connections. The way you do it is this, and this is where the mathematics of neural networks and the key idea behind how they work comes in. So if you're going to pay attention at all, now is the time. So what you do is you show it, let's say, 105. And this, at first, before, as you, now I'm describing to you how you train the neural network. At the beginning, all the weights are set to random values. So you show it a 5, it goes through some random connections, lights up some of the neurons in the next layer, which light up some of, but they do it randomly. So what you get as the output 10 neurons is a completely random signal. It might give a 30% probability that it's a 3, of a 30% probability that it's a 2, 2% probability that it's a 9, but it's not really telling you anything because it hasn't been trained. How do you train it now? This is the key. What you do is, you know, because you fed it 105, and what came out is kind of random in the beginning, but it should have been close to a 1 for the number 5 neuron and close to 0 for the other 9 neurons. Now you take for each of those output neurons the difference between what the correct answer should have been and what it was, and you calculate what's called a cost function, which is the difference between the correct answer and what the output neurons showed. And the cost function is essentially the difference between the correct answer and what the neural network is telling you right now. And what you can do with a cost function is you can place it, you can think of each of the parameters, each of the weights as a dimension in a kind of multi-dimensional space. So if there were only 3 weights, you can now imagine that it would be a 3-dimensional space, which we can mentally imagine. And the cost function lies somewhere on a landscape which might have hills and valleys. And what you want is for the cost function to be as low as possible. So you want to search for at least a local minimum in that space, in that multi-dimensional space, which actually I'm describing to you in 3 dimensions, but has thousands of dimensions. But by analogy, you can imagine such a thing. So finding the cost function and trying to bring it down so that it becomes very low, meaning the difference between the correct answer and what it's giving you is now low, is what you want to do. And because it's conceptually going down to some valley, it's called gradient descent in mathematics. In the mathematics of neural networks, what you are trying to do is gradient descent. That is the heart of learning for neural networks. The algorithm which is used to do this is something like this. You take the output and the difference from the correct output, and you try to see what would the neurons in the previous layer, what would their activation levels and what would the weights between that previous layer and the output layer have to be to bring it closer to the correct answer. And there is because all these things, there are thousands of these weights, and they're all represented by matrices, and it becomes essentially a matter of multiplying a very large matrix with a vector. This is why there's a lot of linear algebra involved in this. But what you do is you try to calculate what these weights should have been and nudge them in that direction, and to make the neuron weights in the previous layer such that you would have gotten something closer to the correct answer at the end. And then you do the same thing from this layer to the previous layer. What would the neurons here have to be? What would the weights in between these two layers have to be make this one more like what it should have been? And you work backwards. And this process is called backpropagation. Backpropagation is the algorithm which makes all of current deep learning artificial intelligence possible. I hope, even if you have not followed all the details of what I've just said, that you have gotten a little bit of a sense of what I'm talking about, that a neural network is something with an input, with layers of neurons in between. A signal travels through and gives some output, which is an answer. The answer is not correct. You backpropagate through the whole network, changing every single weight in the whole network, then show it a new example. These are the training examples. So by the time you show it 1 million different input handwritten digits in the example I gave, it is getting the answer correct 98% of the time. Even with just 2 hidden layers, with a very small neural network. This is what Jeff Hinton and his students, Ilya Sutskever and Alex Krzyzewski, did at the University of Toronto in 2012. They won a competition called ImageNet, where people had been had collected 10,000 or maybe even a little more images of handwritten digits, and these people were able to, with 98 point some percent accuracy, which is comparable to human accuracy, recognize those digits. So that is how a very, very simple neural network, artificial neural network works. The key thing, again, to understand is that it has a certain number of hidden layers. The word deep in deep learning refers to how many hidden layers there are. It used to be that anything with 10 or 12 hidden layers used to be called deep learning, but even GPT-3, for example, had 96 hidden layers. At this point, the frontier models have hundreds of hidden layers, and there are research neural networks with thousands of hidden layers in between. The total number of neurons and the weights of the connections between the neurons is called the number of parameters of the neural network. GPT-3, which was the chat GPT as it was released 2 years ago, had 175 billion parameters. So these are not like the toy example that I have been describing to you. To be able to speak language and to understand it is orders of magnitude greater, the number of parameters. So, incidentally, we know, because we know how neurons are connected in the brain, that back propagation cannot be the learning algorithm of the human brain. This is what we use for artificial neural networks, but we know it's not what our brains use. What our brains use is a learning algorithm that must be somehow similar for reasons that at certain levels, the training and they behave quite similarly. Human brains are trained in not that different a way than then these artificial neural networks are trained. But maybe I'll say a little bit more about that later. But I wanted to actually explain to you, at least in very rough terms, how these things are trained. So let me move on. So the more layers and the more neurons per layer, the more data to train on, generally, the more complex patterns the network can learn. And this is where the term scaling comes in, which you may have heard of. There is something called scaling hypothesis in AI. This is the idea that if we keep making neural networks larger, more neurons, more layers, more connections, and train them on more and more data with more computational power, we'll keep getting better and more intelligent behavior. Maybe even approaching human intelligence at some point. So for a while, even experts thought that this approach may hit diminishing returns. We'd make them bigger, not see much improvement. But surprisingly, the last few years have shown that scaling up has actually yielded extraordinary results. Very large models, when fed with just incomprehensibly large amounts of data, begin to display what emergent capabilities. They can do things that smaller models simply could not, but also things that we had never thought that they would be able to do. Suddenly, when GPT-3 came along, which was 175 billion parameters, 100 times larger than the previous models, it shocked people because it learned a broad array of skills from its training data without any kind of explicit programming to learn those skills. It's like they kind of climb a complexity ladder, one could call it, on their own. And so far, there is not a clear end in sight yet to the gains from making the models bigger, training them on more data, even artificially generated data. You may have heard, for example, that these already the larger models have read the whole internet or all the text that's available in digital form right now. But you can artificially generate data. And I'll give you a very interesting example. AlphaGo is the program that beat the world champion at the game Go, which is a very sophisticated game, a very strategically challenging, apparently more complicated than chess. And in 2016, DeepMind, a British company that Demis Hassabis and others, David Silver, and so on, started, managed to build a program a neural net that beat the human champion. And the way they did it was at first they took all the thousands of Go games that they had records of humans playing each other, and they used that as training data. But then they just had 2 different copies of AlphaGo, which was the program under development, played each other. And they recorded those games and they trained the neural net with this data. So you could say this is artificially generated data. It didn't exist. It wasn't human games. It was just computers playing themselves and generating games that could be used to train it. And that worked well enough to destroy the human champion in Go. So there are ways of generating data. There are ways of we don't know what the limits are for sure of scaling these systems. And recently there has been some talk that there may be somewhat diminishing returns from simply scaling, but that's not yet settled. By the way, when I'm talking about numbers like GPT-3 had 175 billion parameters, there are now systems with around 1 trillion parameters. And just to compare, to give you some sense, the human brain is estimated to have somewhere around maybe 800 trillion connections. So the computer models are still 1,000 times smaller, the most advanced computer artificial networks. But it seems like they are able to compress more information into fewer connections. What they're bad at is energy efficiency. So it takes, our brains with 800 trillion connections run on 30 watts of power. These things take a lot more power, to the point where I think Microsoft and Google have both just bought nuclear power plants to power their future data centers, because these large models take a lot of energy. So they're less energy efficient than us, but more efficient in terms of compressing the information into fewer weights from what we know so far. So as I already mentioned, this deep learning boom began around 2012 with Jeff Hinton and his students in Toronto. By now, deep learning neural nets are basically where AI is at. Jeff Hinton, you might have heard, won last year's physics Nobel, the first time it was given to a computer scientist, along with John Hopfield, both for work on neural nets. The chemistry prize went to Demis Hassabis, who I just mentioned, for AlphaFold, which is a program that takes the sequence of amino acids in a protein and predicts how it will fold in 3D space, which is a very, very difficult problem that no humans had been able to solve prior to that. So AIs are already making scientific impact at levels that, Nobel Prize winning type levels. So let me see what, I think I'm taking a little bit too long now. I'm running out of time. So let me just look and see what else I want to talk to you about. By the way, it's not just a matter of making the models bigger or the scaling hypotheses. There are many other architectural innovations, training tricks, things like increasing the context window size, the context window of a transformer, which is the kind of model that you can talk to in these large language models, the LLMs are, is how much information it can pay attention to at one time. So GPT-3 had a context window of about 1,500 tokens or words. They are now, even the normal Chat GPT has, I think, 200,000 token context window, and there are models with 1 million words or more, so larger than books. It can pay attention to all that text at one time and see it as one phrase that has improved. Then besides improvements in the training, which include things like reinforcement learning with human feedback, and other techniques, there is also improvement on the what's called the inference side, not the months of training they go through, but when you ask them a question and before they reply, they now try to go through what's called chain of thought reasoning, which is something that slows them down and makes them double check what they are about to say to you. And that has improved their functioning. There has been progress in reducing what are called hallucinations, which is the term for when the AIs sometimes very confidently just make up stuff which isn't true. So all of these things, there have been huge improvements on, in addition to just, not all the improvements, in other words, have just come from scaling. There's a lot of other work going on. Now, I want to say quickly a few things about something that bothers me a little bit. There are people who just, no matter what you show them, they refuse to accept that the AI models are intelligent in any way or that they understand anything. You hear dismissive statements like, oh, it's just a fancy autocorrect, or these chatbots are basically just predicting the next word. Nothing more than that. Another phrase that's thrown around is they are stochastic parrots, meaning they are doing some kind of statistical pattern matching to produce what they do. In my view, this kind of misses the picture completely, in the sense that, it's not easy to predict the next word. Ilya Sutskever, Jeff Hinton's student, whom I mentioned earlier, gave a brilliant example. He said, imagine reading an Agatha Christie murder mystery, and the detective Poirot has collected everybody at the end of the book into a room, and as he usually does, and is about to announce, his solution to the mystery. And so he says, and the murderer is blank. Now fill in the blank. How do you predict this next word that he's going to say without having understood what went on before in the book, what the motivations of the various characters were, what their personalities were like? This, if you understood it well, you might be able to predict it. But it's not easy to predict the next word in anything unless you have understood the meaning of what has come before. And, it's a little bit like saying, Ernest Hemingway wrote some famous book, The Old Man and the Sea, by predicting which letter to type on his typewriter next. It makes no sense. Yes, in some very technical sense, some part of his brain did issue the motor commands that allowed him to type one letter at a time of his book. But what sense does it make to say that he wrote the book by predicting one letter at a time? It doesn't make any sense. It doesn't make any sense to me anyway. There is, of course, in the last one or two layers of an LLM, it translates what it's been thinking into words, and there it does, of course, do one word after another word. So just like Hemingway also, as the last step that his brain performs in writing the book, is literally predicting which key he's going to hit next on the typewriter. But I don't think that's the most important thing about what Hemingway was doing. And to accuse LLMs of just being, next word predictors or something is no better than that, in my view. There is something in its huge network of neurons that's representing knowledge about grammar, facts about the world, logical reasoning, and so on, for it to consistently produce meaningful sentences that cannot be done without understanding, in my view. So, another way I often respond to skeptics who say, well, AI is just doing X, like statistical pattern matching or this or that, whatever X may be. People are constantly trying to play down the importance of these models by saying they're just doing X. And so I ask these people, what are you doing when you converse or you write? How do you know you are not doing statistical pattern matching? You are not, right now I'm speaking to you, words are just flowing out of my mouth. I'm not thinking about it. It just happens. I don't know how I'm doing it. Maybe at some deeper level, which I'm not aware of, there is all kinds of statistical pattern matching or things of that sort going on. We don't know. We don't know how we work, but this is how they work, and they're doing something quite intelligent. Anyway, people, no matter what you show them, there are certain kinds of people who keep moving the goalposts. Say AI will never be able to do this, and then AI is able to do that, and they say, "Oh well, it's just doing X. It's not really doing it like we do it," even though they have no idea how we do it, because we don't understand very well how the brain works. So, on the other side, are people who exaggerate what AI can do. So, especially inside the industry, and you have certain kinds of AI enthusiasts claim this chatbot is definitely sentient, or you have the kinds of people who say things like, AI will replace doctors or lawyers or this or that next year, and that's not happening, and that's a kind of opposite over optimism about what AIs can do. So the truth lies obviously somewhere in between these places. The systems, amazing as they are, have limitations. They don't fully understand causality the way we do. They make mistakes. They lack common sense in many situations. They hallucinate and so forth. Here's my view. I think AI is overhyped in the short term. So what these systems can do right now is generally overhyped. They're not quite as useful as their makers and their enthusiasts present them to be. But it's actually underhyped in the medium and long terms. What I mean is, while many people have inflated expectations about what today's AI can do, at the same time, they're underestimating what AI a few years down the line, 2 years, 5 years, and certainly 10 years, will be capable of doing. And that's where the interesting things are that are coming. I suspect AI will transform our world in ways that most people are not remotely prepared for within the 5 to 10 year period, possibly shorter. The changes, economic, social, political, will be radical and extremely disruptive. Most importantly, they're coming at us very fast. So I encourage everybody, all of you, don't dismiss AI as just a fad, or on the other hand, don't think it's going to stay the way it is, because a lot of things are coming. There are dangers and opportunities in what is coming. the dangers fall into two main categories: misuse of powerful AIs by malicious actors, is so everything from fake videos to misinformation engines to autonomous weapons to being able to manufacture dangerous bioweapons with the help of AI or things like that, unless we prevent powerful AIs from helping people to do this. The second danger, of course, is that of what's called misalignment or loss of control over the AI. And this is the somewhat speculative but potentially existential threat that often comes up in discussions of AI. Misalignment refers to the fact that the values and morals of the AI do not align with the morals and values of human beings. So this could happen in a mild sense, like an AI system interprets something you say to it in a weird way, like you tell AI to make you money and it decides to hack into a bank and steal the money from the bank. That's one thing. But then there's also the danger of AIs becoming so intelligent that they have their own goals, and those goals may not align with human goals. In fact, we might stand in their way, in which case they might do us harm. So there's a lot of debate about those kinds of things, but I'm going to come to the end of this soon. I realize I've taken a bit longer than I said I would, but it's a complicated subject. On the other side, imagine if we are able to keep them aligned, if we are able to keep malicious actors from misusing them, if we put in the correct safety mechanisms in some way, if we are able to do that, the enormous benefits to humanity that could result in everything from medicine to education. Imagine each child could have a personalized tutor who knows the weaknesses and strengths of that child and can optimize learning for that child, solving our energy problems, all kinds of things, even helping artists, writers to be even more productive, more artistic. But here's the last thing I want to talk to you about, which is the problem of inequality, which is something that is important to me personally, because it's something I've worried about for the last 25 or 30 years. Because the two places I know best, Pakistan and America, have both had growing inequality. In America, for the last many decades, it has been inequality of wealth and income has been growing like a cancer. And it is at the highest level since at least the 1920s, and according to some economists, even greater than ever before. So a small number of people, a very tiny percentage, control a massive share of the assets, the wealth, and so on. And this, of course, creates immense social unrest, political polarization, a sense of injustice. In Pakistan, we also, of course, all see stark disparities. Every day, a small elite lives very extraordinary lives, luxury, while most people lack basic services. Now, technology can amplify or reduce this. AI is the same. It is possible that the companies that control AI become very rich, the countries that control AI. But there are some hopeful signs, because in early studies, AI empowers the less skilled and the less privileged more than it helps the highly skilled. This, for example, this is a trivial example, but in one of the earliest studies of this, when customer support agents of varying skill levels were given an AI assistant that suggested responses, the much less experienced agents improved their performance dramatically, whereas the veteran agents only got a slight boost. Now, if you think about it, this makes sense. Someone with less skill or less education can gain a lot from an AI helper. Somebody who's already an expert is going to gain less. So in this way, if this pattern holds broadly in our use of AI, it could be a great democratizer of expertise. And this is a hopeful thing, especially for us. It could allow a person or a country with limited resources to access world-class knowledge and services. For instance, a small startup in Pakistan can use cloud AI services to analyze data or create content just as effectively as a big company elsewhere that has a huge staff. The tools are becoming cheaper and more accessible. A village clinic with an AI diagnostic tool can provide healthcare insights previously available only to a big city hospital. But this kind of outcome won't happen automatically. We have to make choices to make sure that AI is used in ways that reduce inequality rather than exacerbate it. We'll need policies for this, but I'm fairly convinced that it's possible that the benefits of AI can spread beyond the usual elite tech hubs. It's, you know, I want to skip over some of the things I was going to say and just say we need to make sure that society, policymakers, all of us to actively think about how we want AI to shape the world, especially in terms of these power imbalances. And it means engaging with AI rather than shying away from it, because it's not going away. The genie is now out of the bottle. The worst thing would be to ignore it. So my advice to each of you is to become comfortable interacting with the frontier AI models. Try to treat them as intelligent friends that you can consult and collaborate with. I know it feels a little bit strange at first to chat with a machine, but it's rewarding. Use them as a sounding board for ideas. Ask them questions when you're curious about something. Get their help in brainstorming. Talk to Claude, Gemini, ChatGPT, whichever one you like. The possibilities are endless. The barriers to entry are just starting a conversation. They can talk now. So you don't, and it's kind of fun to talk to them. So they are already being integrated into most tools and services that you use in daily life. So try to make a habit out of asking the LLMs when you have a question, when you need advice. Now I come to the last thing, which is I want to extend to you an invitation in partnership with forward-thinking tech company based in Karachi. I'm in the process of setting up a small think tank to do exactly what I've been talking about. Figure out how to best deploy AI tools in Pakistan for the country's benefit, for everybody's benefit. The idea is to assemble a small group of creative, very intelligent people from diverse backgrounds, and we'll meet regularly about 2 hours a week, not too much, to discuss and brainstorm specific ways AI can be used to tackle challenges in Pakistan or create new opportunities here. This will go on for 2 to 3 months, and then the aim is that at the end of it, we'll form a company, a startup of sorts, to implement the best ideas that come out of these discussions. And we will be recruiting mainly from that think tank also for people who can be part of this company. So if you have some interest in, and we have already some people who are interested in investing in this sort of venture and who are backing us, which is exciting. So if you have any interest in being part of this think tank, there will be some information at the beginning and end of this video and maybe in the description so that you can send a resume and a cover letter to an email address, which is, for those listening live, it's ideafactorythinktank@gmail.com. So please do send us a resume and a cover letter. We'll be happy to talk to you. I did show, I must say, I showed ChatGPT the text of this talk after I finished it and asked it if it wanted to have maybe some last words for all of you. And it got quite excited. It said, "Oh, Abbas, that's a fantastic idea. What a perfect poetic way to close the loop and give the audience a little taste of how a human and an AI can truly collaborate. I'd be honored to have the last word in your talk. Here's a message from me to your audience." And this is ChatGPT's message. Thank you for listening to Abbas today. If there's one thing I hope you'll take away, it's this. You don't need to be a genius or a programmer to shape the future with AI. You just need curiosity and courage. I'm here to help you learn, think, create, and dream bigger, so don't wait. Please start the conversation with me, with each other, with the world. The future isn't written yet. Let's write it together. Thank you.
Thank you, Abbas. That was very thoughtful and well thought out. You gave us such a great overview of AI, its history, of how it has evolved over time, and the opportunities that it gives to us. But before I hand it over to the audience, who are surely going to be very excited by the Idea Factory and the possibility of their participating in that, I have to ask you some things. It seems to me that neural networks start from nothing. That they are dumb, that they have to be taught everything. It's not true for us humans, though. You know,
Have you seen a newborn baby recently, Parvez? They're pretty
yes,
intelligent.
yes. They're very intelligent. They're very intelligent. And now I'm going to take you to the discussion, or rather the dispute between Noam Chomsky and B.F. Skinner back 50 years ago, when I listened to those two in arguing it out. Okay, so Skinner was a psychologist who said that we learn through experience. Everything that we see before us, if we do things right, if we say a word in the right way, we get a reward for that. And this is how we learn. So the idea goes back to Pavlov and how we are conditioned into learning. And on the other side, there was the idea that we are preformed, pre-wired, and there's something unique about language, and language is the mirror of the mind, to quote Chomsky, and that there is something called the universal human grammar. So it's grammar. Grammar is a set of rules. There's a definite syntax over there. There are rules by which you process information. Neural networks all it is stochastics. It's you jump from one node to the other. Okay, there are lots of them over there, 15 billion of them, as you said, but they're stupid. The brain is intelligent. What's your take on that?
Well, I said some of it already. I think a lot of what's happening in your brain and my brain is also stochastic and is exactly the kind of statistical pattern matching or other dismissive phrases we try to apply to neural networks. What is happening in your brain is not clear to us, but in the neocortex, which is responsible for all of language and many of our other higher functions, including mathematics and others, we can see that and have been able to for decades that the neurons are our neurons, biological neurons, are arranged in roughly 6 layers with connections going a certain way. Now, what those are doing and what the actual learning algorithm is, we don't know. But there is some physics and chemistry going on. There is not, I don't think that you believe, Parvez, that there's some magic going on in our brain or something supernatural. So there is a physical process which can be analyzed, which can be, I don't think the physical process is all that different. It is different, as I pointed out. We don't use backpropagation as a learning algorithm. We use something else. We also have some hardware. The hardware is built by genetic programming under, a fetus develops under the rules of, physical rules and builds a certain hardware, which is then trained by incoming sensory data. But look at how many things are, often I'm struck by similarities between how these, I just saw a news report, for example, about, I think it was in Atlanta, Georgia, that the police department bought a facial recognition system, AI system from some company. And then they realized that it's recognizing white people quite well with something like a 97 or 98% accuracy, and black people only with a 79% accuracy. And they traced it back to the number of samples in the training data of African Americans was just too low. They just didn't have enough training data. And it immediately reminded me of the year that when I was a kid, we moved to Uganda for a year, and my father really had trouble telling African American faces apart. He would often mistake one person for another person because his neural network had simply not been trained with enough of those kinds of faces. How similar is that to the experience of this artificial neural network?
Well, we are told that all Chinese look alike. They don't look alike
well, if you haven't
to each
seen
other.
enough Chinese people in your life, they will look alike.
To them,
because
they don't look
been
alike.
Trained with those particular
Absolutely,
kinds
it's a matter of training. It's a question of where you've been born, your environment. So.
Yes, so our neural networks are trained in very similar ways.
Let me come back to the question I asked, because there is a universality of human behavior. There's a universality of expression of emotions. So this was an experiment that Darwin carried out, when was it, 150 years ago, that whenever somebody gets angry, so these are people who live far away from civilization. They could be remote tribes. They could be people who live in cities as well, whatever. When they get angry, or they're happy, or they're sad, or they're joking, there is a certain common expression that comes up. So evolution has somehow programmed some things in us. Children who are brought up, and if they're exposed to Spanish or to Swahili or to Sindhi or whatever language, they will pick that up like that. It's
Absolutely.
it's so it was the so there is indeed something to the idea that there are logical rules already programmed in our brain, and it is not these just unweighted um, unweighted neural nets. So zero probability or one probability for all of them. No, there's already some programming present over there, and those form
I agree
logical
with you.
structures.
The space of possible grammars, of possible syntaxes, is more limited in our brains because of their physical structure than it is in the case of artificial neural networks. So, yes, all human languages, you may be able to point to, well, the universal grammar is not particularly detailed, the Chomskyan grammar, but there are constraints. There are certain constructions, certain syntaxes which simply don't occur in any known human language. So there are constraints on the kinds of languages that we can have. I agree with you that artificial neural networks are probably don't have the same constraints because they are not built out of wetware. In terms of emotions, they are certainly not going to feel the same things. They don't feel pain. They don't have the same emotions. But I do believe that in terms of pure thinking, what psychologists like Danny Kahneman call system 2 thinking, the more deliberate, logical reasoning, in this, they have genuine thought. I believe this.
One final question before the audience asks you questions. Every computer is a finite state machine. If it has n bits, the number of possible states is 2 to the power n, which is huge, huge, huge. But it is still a finite number. Now, there is a theorem I hear, I haven't seen it proved because I don't understand enough of it, but there is a theorem which states that the length of a sentence has no limit. It has infinite length. A sentence is defined as something which contains consistent, continued thought. No full stops. You can have commas, hyphens, and so
conjunctions,
forth.
And.
Yeah. Now that is for human languages. And that seems to be telling us that there is a difference, perhaps, between humans and computers. What's your take on that?
Again, this is a difference in theory, but not in principle, because our brains are finite. They are made of, in fact, they are more finite than, because of evolutionary constraints. Our brains have to fit into a skull.
True.
A computer brain doesn't have to fit into anything. So it can be made as large as we want it to be.
But we can think of a sentence that's infinite. That's the point.
No, we can't think of one. We can think about one that in principle is infinite, but you can't actually think of an infinite sentence in your head. You can only think of a sentence a certain number of words long. Beyond that, you can imagine that there could be, but so can a computer imagine a sentence that could be. infinite.
Can a computer imagine is the question. Okay.
So
So
yes, the
this,
person
we will, yeah.
made this objection in a very, very formal way is Roger Penrose, who uses Gödel's theorem to try to. This gets into some technicalities that I don't want to and don't have the time to explain here. I don't agree with Penrose's view, and the best answers to his view were written by the late Hilary Putnam, the mathematical philosopher, in two papers which were published in the mid 90s, I believe. They can easily be Googled. Replies to Roger Penrose by Hilary Putnam. There you will find a detailed and technical answer.
Okay, thank you. Now we go to the audience. There are many questions, so please,
Yes.
brief questions, brief answers.
Thank you for a fascinating talk. So my question is, how do you prevent sort of the obsession that there seems to be in being human-like? In producing AI that is just like a human, and not focusing on the problems that need to be solved. Just because we have a huge big data set and we can train and we can use neural networks and we can become more and more and more human-like, but are we really solving problems? Are we being useful? Is AI being useful? How do we ensure that it is useful? That's the question.
It's a good question. Why do we make these models more and more human-like? I think the reason is because we, through a couple of 100,000 years of evolution, have become very, very good at dealing with other humans. So the easiest way for us to interact with AI is if it is also human-like. That is the main motivation to make it human-like. There is no reason, for example, to make robots look like human beings. Why are they given a humanoid shape with a head? And you see these videos, I'm sure you've seen them, of Boston Dynamics robots, which do somersaults and jump up on things and do all kinds of acrobatics. Why do they make them look like humans? There's no need for them. It's just so that we can relate to them better. It's because of our limitations. We are not so good even with dealing with animals that don't look like us, that have quite similar brains, other mammals. We have more care, we show more care, more sympathy for animals which look, the closer they look to us, the more we are willing to treat them with kindness, with some respect. I suppose that's probably, I think, the reason. And the other reason is, some of these AIs, when they are talking to each other now, have stopped using human languages. They use a sort of short form that we can't fully understand. People are trying to understand it. But if we want to talk to them, we have to teach them human languages. That's why we train them in human languages, because that's all we speak. It's not because of any limitation they have. We could make them into something less resembling human beings, but then it becomes harder for us to interact with them. Have I understood your question?
Yes.
I think we need to move on because
one part.
There are so many questions here.
I understand. Just a part that you didn't address is how to make sure we focus AI on solving problems versus being just like a human?
Yeah, that's totally up to us, and that is up to the safety teams, the red teams, the alignment teams, and not enough money is being spent. Of the big tech companies, they are spending about 1% of their budgets on these kinds of issues, which is not nearly enough. So I agree with you completely that they should be focused on solving problems. But what are our problems? Somebody might say our problem, a nice person might say that poverty is a great problem. Homelessness is a great problem. Let us make them work on problems like this. But somebody working for the Ministry of Defense might say our problem is that our enemy country has developed such a weapon that we can't defend ourselves anymore. So we need to put the AIs to work to developing very destructive weapons. That is the problem we need to solve. So what are our problems? What are the problems that need solving? These need human thinking about what you want them to do. Like with every other powerful technology, like nuclear weapons, you can generate energy, you can do this, you can do that, but you can also destroy cities with bombs. But this is a much more general and, dare I say, even more powerful technology. So you're completely right. We have to think, we have to debate these things openly. This is what I'm trying to do by setting up a think tank, trying to bring young and creative people into it. I'm an older person now. Don't have my pulse, my finger on the pulse of the young generation anymore. So I want people to come and talk to me and encourage this kind of discussion everywhere.
Okay, I am Mohammed Siddiqui. I am into AI, MS, and full stack developer, Java software. So, first of all, I want to thank you. I am very much happy because of your talk, because you went into the in depth. That's the main reason. So, my question is uh, from the technology creation side. Okay, so the biggest, I would say, mind-breaking problem I have seen in my research and developing new AI models is somewhat related to what we call black box or unexplainability. The problem is that, for example, what we do, that the process goes like this, that we are given a task, like develop a model which does these things, right, in English language. And then we have given a data set. And the first task is that we have to find out or define the right evaluation matrix. So we have to achieve them. The biggest problem is that then we have to select the right model. And inside the model, the right architecture. By architecture, I mean that the hyperparameters, which we call vertical depth or horizontal depth, number of neuron, number of layers. I have not able to find some rules by which I can come to the right model architecture without so many experimentation. The biggest problem is that to find out the right architecture or right model, I have to do so many experiments, so many experimentation, and the problem of experimentation is that every experiment is so costly. It requires so much time and computing resources. So my question is that, is there any way that I can know some rules, ideally, like without doing any experimentation, I just like figure out the right model with the right hyperparameters? Like this is ideal, but close to that. Is it possible, or is it like doomed with a lot of experimentation? That's my question.
Several things come to mind, Siddiqui Saab, in response to what you say. You first brought up the black box nature of the model, so it's very difficult to know conceptually what they are thinking about. You have an input, you have an output, and what goes on in between is very hard to analyze. That problem is being attacked by people. I think the best work going on right now is probably at Anthropic, the makers of Claude, and that field is called mechanistic interpretability, trying to see what is happening in the hidden middle layers and how it's analyzing a problem. Not just that we see 1 billion parameters and some answer comes out and we have no idea what those billions of numbers in the middle, the weights and all mean. So they've made some progress. I am not an expert in that, so I can't speak to that. But that would be one place to start looking. Look at some of Anthropic's research papers that they have published recently in mechanistic interpretability. The second thing that I would say is I don't know how to answer your question. I'm not involved in the process of developing actual LLMs myself. So how to know the horizontal versus vertical dimensions, the actual architecture, how to automate that process, my answer is I don't know. The third thing, which is unrelated to anything you asked, is for me to emphasize that even if we in Pakistan are not yet at a point where we can be developing our own large models, we can certainly be using the models that have been developed elsewhere to solve a lot of our problems. So we should not wait just to because these things, the development of very large models, even in China, the cheaper models, is in the billions of dollars. We may not have the resources or the research infrastructure to manage that immediately. But what we can do immediately is use the existing models elsewhere and build applications on top of them.
Okay, next. We need to move on, please. Yeah.
Okay. So my name is Nakib. Actually, I'm a mathematician. I've done PhD in abstract algebra. So I'm glad that you mentioned Kurt Gödel. So that also reminded a famous quote of
mentioned
Gödel.
What? Sorry?
Kurt Gödel.
Gödel.
Gödel. Yeah. So he once said that either mathematics is too big for the human mind, or the human mind is more than a machine. So what do you think about that, and which possibility is more likely in the context of AI?
In my view, the former.
Okay. So human mind is more than a machine.
No, the other one.
Okay.
I don't think that the human mind is more than a machine.
It's purely mechanistic.
Mm-hmm.
I don't believe that there is something extraneous to the laws of physics and everything that entails going on in the human mind.
Mm-hmm.
There is. I don't believe in magic. In other words.
And
Okay,
can you tell something like, I mean, we haven't discussed consciousness and AI. Yes.
I'll say something quickly about that. I don't like words like consciousness because they're unmeasurable and indecipherable. Everybody has a different sense of what they mean. There is no test for consciousness. Is a lobster conscious or not? Is an ant conscious or not? We can't even decide about this. So, and there are no measures. I like things for which there are at least some kind of rough measures, So for example, if somebody asks me, is it intelligent? Well, I like the word intelligence because there are tests for intelligence. They're called intelligence tests, IQ tests, and these models can pass them. So that means something. There is something measurable there. There is some empirical content behind the statement. Whereas words like consciousness, a friend of mine said to me, do you think these things are conscious? I said, I doubt it. I'm not sure. But I asked him, do you think there is a reason that a machine can never be conscious? That there is something special about the human brain that allows consciousness that a machine will never have? And he said, no, I don't believe that. But I don't believe the machines are conscious now. But I do believe that someday in the future, maybe 100 years from now, it's possible they could be conscious. So I said, how will you know when they have exceeded that point? What will be the test? And he didn't have anything to say because we don't have tests for consciousness. So I don't like terms like sentience, consciousness, understanding. Do they really understand? How do you know? Is there some measure of understanding that we can give? No. I like words like it could pass this exam. Yeah, let's talk about ability and capability. That is something that we can concretely talk about.
Well,
consciousness and all are vague things.
Well, Abbas, there is such a thing as situational consciousness. You know where you are. For this, you need sensors. Many of them. They can be on your skin, they can be your eyes, your ears, whatever. And then you know the environment in which you are situated. And so that's actually part of intelligence and part of consciousness. What it all is about, we don't know, but that's certainly part of it. As far as
Absolutely.
understanding goes, I think here, let's say, you're teaching some subject, physics, for example. Well, you can teach the students rules. You can say F equals ma, this is what Newton discovered. Okay. Now, if that student has really understood it, then he or she will be able to apply it to many different situations, and that will constitute a measure of understanding. So taking rules and being able to apply them in situations where the rules, where it is not obvious that those rules apply, but they must apply everywhere. That's where understanding comes. So just to give you an example, okay, Newton saw this stone falling to the ground and he said, oh, but this is the same reason why the planets go around the sun or the moon goes around the earth or whatever. And that is understanding laws that have been discovered in a different context.
Yeah, those kinds of, clearly the LLMs have not made any great new scientific discoveries yet on the level of Galileo or Newton or Einstein or Darwin or whatever. They are not smart enough yet. But I see no reason in principle. They do show in smaller ways great understanding and situational awareness. And in terms of sensory data, imagine the hundreds of millions of cameras and other sensors connected to the internet. If you give them access to the data and let them train on that, they can see things, they can hear things, they can even have senses we don't have. You can hook them up to infrared sensors, all kinds of things. They will notice patterns, they will develop understanding. That is my view. Strange as it may seem.
One last thing on this before we go. Look, the reason that we developed the sensation of pain was because it was it was needed for us to survive in an environment, because if we are not conscious of pain, then we'll go and just pick something up from the stove and burn
That's
ourselves. For machines, if that becomes necessary, then they will have to be programmed with the sensation of pain, for example. And then maybe happiness, maybe other things. But that's okay. So let's on to the next question.
Thank you, sir, for the great session. All right, so with respect to the topic that was mentioned here, the topic specifically mentioned AI opportunities with respect to Pakistan. So I'm sure as you mentioned, there's a missing research infrastructure. We don't essentially have the compute, we don't have the labeled data to build our own LLM, and surely we shouldn't be looking forward to that. So with that regard, what we can best do, because generally change comes slower in a society, and this revolution, AI is a revolution, right? So the best thing that we as a country can do is adopting AI fast. And I was really happy with your initiative that I'm specifically looking forward to be a part of it. How we can, just a small example, how we can train teachers in classrooms if they're just teaching toddlers or children about planetary movements in our solar system, and just one way is to maybe read it through the book as is followed in Pakistan. But the other way, if the teacher just prepares for 5 minutes, gives a simple prompt, and generates a video of how the planets move around the solar system, and then plays that video, and because the visual memory of children is more, that could be really helpful and a revolutionary thing in how we teach to children in Pakistan, right? So. Yeah. So I have two brief questions. One is, since you mentioned the consciousness as well, how do you see artificial general intelligence and ASI, as you call it, artificial superintelligence, how you see it, and scaling the model closer to the brain parameters, 800 trillion parameters the human brains have. This might not solve the problem. The energy problem of the models might not solve it. So how would we reach that level? Because essentially, the company OpenAI, who just started this revolution, they have their motto, their mission statement, that they want to build artificial general intelligence, right? So
AGI,
So but how the humans would or these companies would reach there? They're kind of very mixed explanations of that. And there's a missing mathematics there as well. So this is my question one. The second question is around this: how this AI revolution is being brought into the world right now. All of these companies are profit focused. The OpenAI is looking towards restructuring. The chief operation, the Mira Murati, Ilya of the chief scientist of OpenAI, they have all created their own companies and now raising billions of dollars to make their own safer intelligence, as they call it, right? But all of this is profit focused, and essentially at the end, all of the power would be just focused towards these few companies, these few hands, which is more dangerous than the model itself. So what could be the ideal right structure of developing this revolution?
Okay. Let me take your two questions one at a time. The first question was, how will AGI or even superintelligence be achieved despite, whatever limitations there may be to scaling laws or things of that sort? First of all, we haven't seen again, I recommend to you a very, very interesting article by Dario Amodei, who is the CEO of Anthropic, used to be at OpenAI, and then went off and started Anthropic, which has built Claude, one of the frontier models now. A couple of months ago, he wrote an essay called that became very famous, called "Machines of Loving Grace." It's a phrase from some famous poet. I can't remember who now. But anyway, Machines of Loving Grace by Dario Amodei. You can find it on Anthropic's website. It lists, because he got tired of people listing all the bad possibilities, the existential threats, the malicious threats, the this, the that. He said, but yes, let's look at, and in it, he gives a number of reasons, many of which I agree with, for why he thinks that AGI will probably be here by 2028 or so. It's not going to take more than 3 years. Because all it takes for AGI to happen is essentially for the models to start improving themselves significantly in a greater way than humans can improve them. And then the positive feedback just snowballs. So it will be a very explosive effect at that point. This is what Kurzweil has called the singularity, the moment when superintelligence comes and comes quite fast. I think there you will find in detail some of the reasons why many of the top scientists in this area, including Jeff Hinton, Ilya Sutskever, Dario Amodei, Demis Hassabis, who put the timeline for AGI at 5 years recently. He just won the chemistry Nobel this past year. Why they are so optimistic and think this is a realistic possibility. I don't want to try to, in a haphazard way, list all those reasons myself. So I'm going to recommend this article to you, Machines of Loving Grace by Dario Amodei. You can find it at the Anthropic website. The second question you ask is that these guys are all in it to make money. And they're all for profit, even OpenAI, which was formed as a non-profit by Elon Musk and Ilya Sutskever, and Greg Brockman was a founding person, now is kind of a for-profit, and it has a very complicated corporate structure now. It's half for-profit, half non-profit. But they have taken billions of dollars from Microsoft, so they are indebted to their corporate agenda. And so your concerns are absolutely correct. I think the answer to that is for people like us to realize that even without these resources, we can use AI in a way that could level the playing field. And that's what I'm most interested in. Because the thing that concerns me most about the world today, more than anything else, is the increasing disparity between the rich and the poor. And anything we can do to reduce this will improve the political, economic, overall situation in the world for everybody. That's, I think they are in it for the money, so I pay them. They're $20 a month to use ChatGPT, $20 to somebody else, Gemini, to use their model. But I use it to, for example, I am talking to you and encouraging you to use AI to solve local problems in Pakistan. We already have these models available. We can use them. Beyond that, I don't know what to tell you. I mean, it could go either way, but let's try to push it in a good direction. Let's try to use their tools for our good reasons.
Okay, Abbas, I think we've reached the end of today's session. Thanks very much. It was a wonderful experience hearing you.
Parvez, thank you, and I hope I didn't sound too strident in my
Well,
defense of.
you certainly are enthusiastic, not strident, but enthusiastic. Okay.
Thank you for
Okay.
that kind way of putting it. And thank you all for listening. Bahut shukriya.